So a couple of these we ought to do. Let me erase my chicken scratchings here. All right. So one that kept coming up is number 41, apparently. And looking for my glasses. All right. So in 41, two dots. A small non-conducting ball with a mass of 1 milligram, charge of 2 times 10 to the minus 8 coulombs, distributed uniformly through its volume, hangs from an insulating thread that makes an angle of 30 degrees with the vertical, uniformly charged, non-conducting sheet shown in cross-section. Considering the gravitational force on the ball, and assuming the sheet extends far vertically into and out of the page, calculate the surface charge density of the sheet. Oh, goodness. All right. So here's our sheet of charge, and it's all positive. And it has a surface charge density sigma, okay, which we would like to know. We've got a string, a ball, and that has probably a positive charge on it. And let's see, theta is 30 degrees. And Q is some bizarre little number. 2 times 10 to the negative 8. Very good. All right. And we'd like to know, what is sigma? All right. All right. What are the forces on the ball?
MG.
Good old MG. What else?
Tension.
Tension in the rope. What else?
Electric.
All right. So this is not totally foreign to us. Okay. Now, what to do next? Break it down. Okay, so this guy is theta. I'm going to call this Ft cosine, Ft sine. And so if this guy is in static equilibrium, my claim is that Ft cosine theta equals mg. And that Fe equals Ft sine theta. All right. I don't see a sigma anywhere in sight in any of those equations. Say, why is this little positive ball experiencing an Fe on it? The field coming off of this sheet of charge. Now, if you go back a couple of pages in the book, the sheet of charge, let's see, planar symmetry, there it is. The E field for a sheet of charge is sigma over 2 epsilon naught. So E field due to a sheet of charge is 2. Mr. Everly's losing his mind. Sigma over 2 epsilon naught. Yes, I'm losing my mind.
2 over sigma.
Yeah, no kidding. Much better. Very good. All right. Wait a second. If I know what the E field is right here, how can I figure out how much force is on that charge? What's the definition of E field?
F over Q.
F over Q. All right. So E is equal to F over Q. So F equals EQ. So would you agree with me that E times this charge right here is equal to this force? I'm starting to feel better about this. And what is E due to a sheet of charge but sigma over 2 epsilon naught? starting to feel better. We know what the charge is. We know what epsilon naught is. Crap, I don't know what Ft is. How am I going to get Ft out of there?
mg divided by cosine.
Oh, okay. So I know that Ft is equal to mg over the cosine of theta. And I know all that crap. So I'm going to say this is mg times the tangent of theta, because I'm going to have a sine on top and a cosine on the bottom, so I'm skipping the Christmas rush. And this is going to be sigma q, be careful here, that's part of the diagram. This will be sigma q over 2 epsilon naught. So let's do it. Sigma is equal to 2 epsilon naught mg tangent of theta all over q. Okay, be careful. Make sure that the mass is in kilograms. I think they give us the mass in micrograms or some silly thing like that. Yeah, milligrams. So they give it to us in milligrams. So mass is 1 milligram. Therefore, it is 0.0010 kilograms. Okay? So watch out. Make sure your units are right.
Like smaller than that.
Milli?
Because grams, that would be grams, wouldn't it?
Oh, you're right. Now we're in grams. We have to go further. Holy moly, you are so right. So it's like 0.000001 kilograms. Oh my goodness. So probably scientific notation is a good idea here.
10 to the negative 6.
Yeah.
I thought that was micro.
Oh, I forgot gravity.
Well, we're going from, like you pointed out, we're going from milli to kilograms. Okay.
Oh, yeah, yeah.
So you can say microkilograms, but that would be bizarre. All right, so watch your mass. Of course, charge is going to have to be in coulombs. And they give us the charge of that little guy as 2. Oh, they gave it in coulombs. Oh, that was nice of them. So the only pain is the mass. Make sure you get the right mass. So obviously, that's where I would have messed up. All right, so not a terrible problem. Remember, you have notes. This is in your notes, right? And if you need to come up with it quickly, like on a test, you could use Gauss's law and come up with it fairly quickly because you, again, each night you read your notes. All right, so that was 41. Next. Did we need to do 42? Let's do it. Okay, so 42 is the answer, right?
Yes.
Life, universe, everything. Here comes the question. The figure shows a very large non-conducting sheet with a uniform surface charge density given. It also shows a particle of 6 microcoulombs. Both are fixed in place. D is the distance between them, 0.2 meters. At what positive and negative coordinate on the x-axis, other than infinity, is the net electric field of the sheet and particle 0? Okay, so here we have x and y axes. Here we have a charge that is positive. Yeah. So a little positive chargey there. Over here we've got this sheet of negative charge that goes on forever. Okay, sigma is a given value, negative 2 microcoulombs per square meter. So I'm going to say negative 2 times 10 to the minus 6 coulombs per square meter. And then this guy, Q, I think they used a capital Q, didn't they?
Yeah.
Oh, they did. 6 times 10 to the minus 6 coulombs. All right. Okay, so let's play the game here. Put Ralph in the center. He's a little positive charge. He's going to be repelled by the point charge, attracted by the sheet. That's probably not a good spot for Ralph if we want E equals it. We put him out here. That's a possibility because we know the E field due to the sheet doesn't change with distance. it doesn't matter if we're 3 centimeters from the sheet or 3 miles from the sheet. The E due to the sheet is sigma over 2 epsilon naught. Okay? The E due to a point charge. That you have memorized, right? What is it? KQ over R squared. Now, if you don't mind, last hour I put the K in there and then realized I also had an epsilon naught. So if you don't mind, instead of saying K, I'm going to say 4 pi epsilon naught. And we're going to let those epsilon naughts cancel out because they're mean little dudes. And we're going to say, okay, here's R squared, and we'll put Q on top. So I've got K Q over R squared. I want to know where those guys are equal and opposite. Okay, so the E field due to this and the E field due to this must cancel out maybe here, maybe out here somewhere. Okay, we're calling this D, and it's like 0.6 meters or some silly number. Let's see. 0.2 meters. All right. They change it later to 0.8. Okay, so I'm going to claim that E1 and E2 are equal and opposite. Is that okay, Stephen? I put absolute value signs around them just for you. Okay. So I'm going to say sigma over 2 epsilon naught has to equal Q over 4 pi epsilon naught R squared. And I'd really like to know what R is. Where's this going to happen? So, Y and Y. So I'm looking at 2 pi epsilon, or sorry, 2 pi sigma divided by Q equals R squared. Double check my algebra there, because I might be losing something. I guess not. I just had a weird feeling I was losing something.
Might be 1 over R squared.
Oh, you're right. I have to flip it, don't I? Oh, Evelie, you nitwit. I had the weird feeling like I was doing something wrong, and I was. Hang on. Back this trolley up. All right, so we need him on top. So let's say that we've got on this side Q, and over on this side we've got 2 pi sigma. All right, now I'm feeling so much better. All right, every now and then your spidey sense starts tingling, and you have to pay attention to it. Ever read Spider-Man? They don't do the spidey sense much in the movies, do they?
No, not really.
He had this sixth sense that something was about to happen, and he'd jump out of the way, and something would happen. All right. Anyways, let's do it. Put your numbers in and have at it. So Q 6.00 times 10 to the minus 6. On the bottom, 2 pi times sigma, and we said that's 2 times 10 to the minus 6. Oh, here's a nice Y. So it's the square root of 6 over 4 pi. So a quick punchy. 6 divided by the quantity 4 pi. Take the square root, and you get 0.691. Now, do we get 0.691?
Mm-hmm.
No, we don't. We get plus or minus.
Oh.
This is a square root. So our charge is at the origin. So it's out here at 0.691, and it's out here. So D is 0.2. So we could definitely have a spot out here where it works. Then in part C, they say, let's make this 0.8. So we move the sheet out and make this 0.8. Now, the 0.691 is in between. The negative 0.691 is in between. The other 0.691 works fine. This one won't work because it's in between. And we know that in between is a bad spot for Ralph. So once again, the difference between physics and math. Okay? We get two solutions. One of them doesn't make sense, so we discard it. In math, you discard nothing. In physics, you have to make sense of things. And it has to make sense. Okay. And that's a little bit of a joke, but it's also true. Like I've said before, the difference between a theoretical mathematician and a theoretical physicist. The theoretical physicist owns a wastepaper basket. Yeah. All right. So the answer is 0.691 meters and negative 0.691 meters. And then for part C, it's just 0.691. The negative one doesn't work. All right. Taking a look at number 51, yes? Mm-hmm. What a piece of work. Okay. I added this one on. I didn't do this one beforehand. I've added this one on for more Gauss's law practice. This thing goes out to part H. Holy moly's oh moly's. All right, let's do it. So, 51. I need to conserve my space here. So if I go off the board, Kellen's going to be upset with me. All right, so we have this sphere inside. It's a solid sphere of radius 2 centimeters, concentric with a spherical conducting shell. So I'm getting the read from this that the sphere is non-conductor because it's got this uniform charge distribution, but the outside is a metal shell. So I've got this like little plastic ball here, and then this metal shell that goes around it. Okay. Just to keep things from going crazy, I'm going to make the center ball a little bit bigger. There we go. So I know this is a, they're calling this B, but it is really 2A. And then they're calling this C, but it's like 2.4A. It is. Okay? The outer one is a conductor. The inner one is not a conductor. The space here is, vacuum or empty. All right, so let's have at it. A is 2 centimeters. 0.02 meters. The sphere in the center has a Q1 of 5 femtocoulombs. So it's plus 5 times 10 to the minus 15 coulombs.
That wasn't in the back of the book.
It was on the inner cover of the book before it was rebound. Or Google. All right. Next, Q2 is negative Q1. So the metal shell has the same charge as the inner sphere. The only difference is it's negative. All right. So then they ask you a million questions. First is A. What is E when R equals 0? What'd you get?
0.
0. Why?
Because it's acting all from opposite.
Oh, yeah.
direction. Yeah.
And if you try to draw a Gaussian surface inside there at R equals 0, how much charge will it enclose? 0. So there's really, there's really no other answer we can give. B is really the hardest one of the bunch. B is a pain. The rest of them kind of go kind of quickly. But B is the widowmaker. Are you ready? Okay. So B is saying if we are at half of A, if we're at half A, what is the E field? Okay, so here it comes. This inner guy has a uniform charge distribution all through him. Okay. We're going to say at half A, we're going to make a spherical Gaussian surface. Okay, I don't know if you can tell that that's red, but I tried to make it red. And he has a radius of A over 2. Okay, switch back to black, and we're going to say, all right, if I want to find the E field there, let's go Gaussian, baby. Okay, so there's definitely some positive enclosed charge. E is not equal to 0, but can we say that E is the same everywhere on that dotted red line? By symmetry. You okay, Amanda?
Yeah.
All right. So I'm going to claim then that I can pull out the E. What I have left then is the integral of dA, which is the surface area of my red sphere. So the surface area of my red sphere is 4 pi r squared. So I'm going to say 4 pi r squared. In a minute, we'll put A over 2 in place of r. So just chill out for a second. Okay, equals the enclosed charge. Okay, the hard part of this is the enclosed charge. So how much charge does it enclose if we have a sphere of half radius? Assuming all that charge is equally distributed all the way through that inner sphere. We'll say, look, charge density is the total charge divided by the volume. Okay, volume of the entire black sphere of radius A. So I'm going to say, all right, it's Q1 over 4/3 pi A cubed. The enclosed charge has got to work the same way, except the volume of my red sphere is 4/3 pi A over 2 cubed. So, y. And, believe it or not, if I cube the top and bottom in these parentheses, I got A cubed on top and an 8 on the bottom. Okay. So, Q enclosed is Q1 over 8. Are you okay with that? Because Q enclosed divided by 1/8 is 8 times Q enclosed. Divide both sides by 8, and we have the enclosed charge in our red sphere is Q1 over 8. Okay? You good?
It's a doozy.
This is a doozy. Part B is a doozy. All right, so here we go. Should I rewrite this? Let's just rewrite it. Okay, if I replace r with a over 2, I've got a squared over 4. I'm trying to think if I want to do that or not. I think I do. We're going to keep moving forward here. So, because we know what a is, right? Yeah, point. Oh, okay, that's good. That's good. That's good. So, and then this is going to be Q1 over 8. And I'm going to solve this puppy for E. Very good. All right, so we're going to lose this. And here we go. E is equal to Q1 on top, 8 pi epsilon naught, a squared on the bottom. We win. Punch that out, and I'm fairly confident we will have the right answer. say that was a doozy? I have to agree. I am out of room here, so I'm going to say, okay, I've got Q1, which is 5.0 times 10 to the minus 15. On the bottom, I've got 8 times pi times 8.85 times 10 to the minus 12. And then I've got a squared. A is 0.02. We'll tally up the sig figs when we're done. And I don't have the answers up, but you can check it out. See if it comes out when you punch it out. All right. Next step. Okay, like I said, once we get part B done, this is a much happier process. Because part C says, what if R equals A? What if we're right on the surface of this guy? Now, there's two ways to do it. We could go Gauss's law, or we could remember that if we're outside of a spherical distribution of charge, that we're going to treat it like a point charge. Okay, so part C, if we say epsilon naught integral E dA equals Q enclosed, our Gaussian surface is fitting this guy like a glove. In other words, our Gaussian surface is right on the surface of the sphere. And so the enclosed charge is just Q1. Whew, thank goodness. And this gets much, much, much nicer. Okay, so we'll say, all right, this is epsilon naught E. The integral of dA becomes the surface area of our sphere, which is 4 pi a squared. Q enclosed is just Q1. Solve it for E. So we've got E equals Q1 over 4 pi epsilon naught a squared. And so that a squared there is really r squared, right? This is the E field due to a point charge. Punch it out and you're okay. So part B is just intimidating as heck. And it makes you say, you know, I don't want to do the rest of this. It makes you lose the will to do the rest of the problem. You kind of like, ah. All right. Part D. At 1.5a. Okay, at 1.5a, what are we going to do? Our Gaussian surface is now this. How much charge does it enclose? Q1. What's its radius? 1.5a. It's the same solution as C, except we're going to put 1.5a at the bottom instead of a. Okay, there's really no difference. It's enclosing just the inner sphere. Okay, should I write that one out, or are you okay? Yes, write it out?
No.
Oh, okay. I thought I saw a nod there. All right, next. What if it's 2.3a? All right, now, I don't remember this one. This one, we know that the inner sphere B is 2.4. So if R is 2.3a, we're still out here, aren't we?
No, I think you're in.
Are we in it now?
Yeah.
Okay, I'm misreading this. Oh, C is 2.4, B is 2.0. Oh, okay, you're right. So actually, I want this guy right here. All right, I am in the middle. Life is good. Okay, so I'm in the metal. What's the electric field when you're inside a piece of metal that's isolated? Zero. Move on to the next problem. And then it says 3.5a. Okay, Gaussian surface out here. Okay, how much charge is enclosed by that red dotted line? test says no charge enclosed. Is that true? No net charge enclosed. The word net's kind of important, isn't it? So if the inner sphere contains charge Q1 and the outer sphere has a charge of negative Q1, then when I add up the enclosed charge inside this big sphere, I get 0. So what's the E field out there? 0, according to Gauss's law. When we write out Gauss's law, we would say, all right, if Q enclosed is 0, then the E field is 0. Okay, because the net flux through that dotted red line has got to be 0. Okay? Answer, 0. Okay? Then, what is the net charge on the inner and outer surface of the shell? All right. Back to the dotted line that's inside the metal. Okay? So I'm trying to point this one out, Kellen. Inside the metal, we have a dotted line. E equals 0 at that dotted line. How much charge must it enclose? Okay, go back to Gauss's law right here and say to yourself, okay, if E equals 0, what must be the enclosed charge? 0. Because dA is never 0, right? The area is not 0. Epsilon naught certainly isn't 0. The only option is the enclosed charge must be 0. So what charge must be on the inner surface of this shell? Okay, back up a second. This dotted line must enclose no charge, no net charge. I have a shell, I have a sphere in the center with a charge of plus Q, Q1. The shell must then cancel out that charge so that the total charge enclosed by my shell that's inside the metal must be 0. So the inner shell contains negative Q. Now, go back to what you know about charges, right? This is a conductor, and inside that conductor, we've got a charge plus Q1. What are the free electrons in that metal going to do? What? Try to get toward it, right? They're going to take a station right on the inner surface of that metal shell. Okay? So how much charge is on the outside? If the total charge on the metal is negative Q1, and all of that Q1 is located on the inner surface, how much charge is left to be located on the outer surface? Nothing. There you go. So number 51 is not bad once you get past part B. If you get past part B, this puppy cruises. It's super easy. But part B is a pain in the backside because you got to figure out how much charge is located within a shell that's inside of a sphere that has a uniform charge distribution. Don't ask me to say that twice. Okay. So, what I would like you to do in the next few minutes, you were taking care of number 11 on your whiteboard. I'd like you to take care of number 31. Meanwhile, before you do that, real quick, I'm going to pass out the review for the test. Officially, the test is on Thursday. After 0 hour on Thursday for you guys.
For that 0 hour, are we going to start the next unit?
If you have questions, and if I can help you, no. But if everyone sits and kind of looks at me and says, I got this, Mr. Everly, I got this, then I'll move on to the new unit, which is electric potential. It's one of the tougher units in this 6-unit odyssey that we're on. So it would be Unit 3, the 3rd unit in E&M, and my personal toughest one. The rest of them aren't so bad, but we really have to get the idea of potential, the idea of voltage down. And if you even take a look at the book and try to read the book, they don't define what potential is. They skirt around it, they play with it, it's smoke and mirrors. So I'm going to try to take the mystery out of potential, try to make it something you understand. But that is, to me, the toughest unit. So I don't mean to intimidate you on that one, but that's one you really have to pay attention to. All right, so I'm going to stop the recording because you guys are going to work on some stuff.
Bye, Kellen.
Bye, Kellen. Hope you're having fun in Washington, D.C. Hope you meet Donald Trump.
Don't miss you.
No.
Say hi to Bernie.